Okay, for this video we'll be constructing the Lewis structure for HCONH2. And before we do that, we should figure out how many bonds this molecule should contain. So let's do that. Number of bonds equals the demand minus the supply all over 2. So what is our demand? Our demand is to satisfy each atom to have a noble gas configuration. We should know hydrogen follows the duet rule and can only have 2 valence electrons. So this hydrogen over here has 2 of them, so let's just say 4 because 2 plus 2 is 4. Carbon, oxygen, and nitrogen all follow the octet rule, so we can write 8 here. Add all these up, it should give us 30. So that's our demand, is 30. Minus our supply, which is how many valence electrons each atom can actually contribute to the molecule. And we know hydrogen's in group 1, so it's 1 valence. We have a total of 2 hydrogen over here, so we can just write 2, because 1 plus 1. Carbon is found in group 14, so 4. Oxygen group 16, so 6. Nitrogen group 15, so 5. Add all these up, and that should be 18. So 18. We'll divide that by 2, and we'll find out 12 divided by 2 equals 6. So this molecule should contain 6 bonds. Now what I have down here enclosed in brackets with double-sided arrows is resonance structures. And these resonance structures all contribute to the resonance hybrid, which is a combination of all these structures. However, some structures contribute more than others, and we call that the major resonance contributor, which best represents, I guess, what the molecule will actually look like in the end. So I'll show you which one is the best, and I'll give you the rules. So let's just start with the first structure. So we have 6 bonds to give. Let's do our hydrogens first, because we know they only have a single bond, so it has the duet rule. Let's finish constructing our molecule. So now all of our molecules are connected. However, we have one more bond to give because 1, 2, 3, 4, 5, 6 minus 5 is 1. Now we can either put the double bond between the carbon and the nitrogen or between the carbon and the oxygen. Let's just put it between the carbon and the nitrogen first. Now we need to finish off giving the oxygen its lone pairs. So it has an octet. So these are just lone pairs of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, which is our supply. So that's perfect. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So they all follow octets. But now we need to give these atoms a formal charge, and this is the formula I tend to use, which is valence electrons minus our lone electrons plus the number of bonds. So let's do that. Let's look at this oxygen first. Oxygen is in group 16, so it's 6 valence electrons, minus our lone electrons, which is 1, 2, 3, 4, 5, 6, plus the number of bonds has a single bond, so 6 minus 6 plus 1, which would be 7. 6 minus 7 equals -1. So this oxygen right here has a negative formal charge. So let's do that. This has a negative. Look at this carbon. It has a total of 4 bonds with no lone pairs, so it's automatically 0, but I'll still show the formal charge. Valence electrons, it has 4, minus our lone electrons, it doesn't have any. So 0 plus number of bonds is 1, 2, 3, 4 bonds. A single, 2 singles, and a double. So 1 plus 1 plus 2 is 4. 4 minus 4 is 0, so we know that's 0. Let's look at the nitrogen. The nitrogen is in group 5, so or group 15, so 5 valence electrons minus our lone electron, which is 0. And it has a total of 1, 2, 3, 4 bonds. So we'll add 4 right here. So 5 minus 4 is 1. So this nitrogen has a positive charge. So now what I'm going to do is redraw this structure the same over here. So when I make the resonance structure, it doesn't get all messy and confusing. So all I'm doing is just redrawing our structure. It's the exact same. add in these lone pairs. Meant to make another colon, so these are lone pairs. There's a colon. There we go. So don't forget our charges. This oxygen has a negative, this nitrogen has a positive. Now, what we are going to do is the method called electron pushing. We are either going to move electron pairs, so we're either going to move electron pairs to make bonds, or we're going to be breaking bonds to create lone pairs, and this will make a lot more sense when I actually do it. So what we like to do is go from a region where we have the negative formal charge towards the region of a positive charge. So we can see our negative formal charges on the oxygen, so what we're going to do is take these lone pairs of electrons and make a double bond. So when we make this double bond here, we are also moving this charge. So right now, this charge would move on to the carbon. But first, let me clean this up so it looks nicer. So let's remove those and draw in a double bond. Okay, now we have a total of 2, 4, 6, 8, 10 electrons around this carbon, and we can't have that because that violates the octet rule. So what we need to do is break a bond. So we're going to break this double bond and put a lone pair on this nitrogen. So let's do that. So we broke that double bond between the carbon and nitrogen, and now we are moving this right here. Keep in mind, this charge is still moving. Now it is on the nitrogen. And we can see here we have a positive and a nitrogen on this nitrogen, a positive and a negative on this nitrogen, so we know they cancel out because 1 plus negative 1 is 0. So this is what our other resonance structure looks like. Now, this last molecule is very unconventional, is rarely ever drawn, so you wouldn't really need to draw it because it doesn't really contribute to the molecule that much. So let me just draw it real quick. Connect our hydrogens. We'll redraw our molecule. So I'm going to redraw this one right here. So let me just do that. There we go. And I need another bond between here. And another lone pair on that nitrogen. Okay, so I just redrew this molecule over here. Now, this is why I say it's really unconventional. What you can do here is you can break this bond, this double bond here on this oxygen, and put it on this oxygen right here. So you're breaking this bond between the oxygen and carbon and putting the lone pair up here. So let's do that. And don't forget, since this molecule was neutral, and we added negative charge because we took a lone pair and put it on a neutral, so that will give this oxygen a negative charge. You can check by doing the formal charge, so let's just do that. Valence electrons is 6 for oxygen minus the lone pairs, which is 1, 2, 3, 4, 5, 6, plus number of bonds. It has a single bond, so 6 minus 7 equals negative 1. That is why there's a negative right here. Now, here's the reason why I say it's unconventional. This carbon has a sextet. It has 1, 2, 3 bonds, so this would have a positive charge. And we can do that by doing the valence, or the formal charge formula, which is valence electrons, which is carbons in group 14, so it'll be 4, minus our lone electrons, which there's 0, plus number of bonds, it only has 3 single, so that equals 1, a positive 1. This carbon only has 2, 4, 6 valence electrons around it, that's why it's called sextet, and it doesn't really contribute to the resonance hybrid as much, but let me show you how to determine which one is the best. So if we look down here at these rules, let me move them up here. Okay. First off, octet is the best. So the octet rule overrides all of these. So octet is always the best. And we saw here that this carbon only has a sextet, so we automatically know this is not the major resonance contributor. So that one's off. Now, Let's look at the next one. Least separation of charges. This one has a plus and this one has a negative, and this one has no charges, so that one's off. So the last one is negative formal charge on most electronegative atom, but we don't have to even worry about that because we already canceled these two down to give this one. So this would be your major resonance contributor. This would be your second best, and this would be your last. So all of them together would be the resonance hybrid, so that'd be what that molecule actually looks like. However, this one contributes most to what the molecule looks like, and that's it for this video.